We'll figure out sort of where to sit. I'm fairly sure. And first of all, thanks a lot also for your kind attendance during our session today, because I think we're also discussing one of the most interesting topics that we could currently have in terms of when we would actually do a quantum leap and when quantum advantage would also come. And I'm very pleased to be here today together with Axel, Jerry, as well as Loïc, also on stage and discussing this very interesting topic. We'll first give also an introduction to ourselves. I'll quickly introduce myself, Henning, partner from McKinsey, also from the office in Frankfurt. Been with McKinsey for the last 13 years, and since the last 5 years, also our global lead for our activities in the quantum space. Maybe, Loïc, you want to go ahead with a bit of an extended introduction, also saying a bit about what you're doing, what your company is doing in this interesting space, and then we take it from there.
Sure. Thank you very much. I'm very happy to be here with all of you for this discussion. I am Loïc Henriet, CTO at Pasqal. Pasqal is a French company building quantum computers and operating quantum computers, implementing algorithms on those quantum computers for our partners and clients. Our technology is based on neutral atoms, so single atoms that we manipulate with the laser light. And we use those atoms as qubits, building blocks, to actually implement a quantum algorithm. The technology has been developed in France at Institut d'Optique Plateau de Saclay, in a research lab with Alain Aspect, Nobel Prize in Physics in 2022, as well as Antoine Brouès and Thierry Lahaye. And for the last 7 years, we've developed this technology, industrialized it, and installed quantum computing machines with HPC centers all around the world. So that's what we are doing at Pasqal.
Jerry, you want to go next?
Great, thanks a lot for having me as part of this panel. So my name is Jerry Chow. I'm an IBM fellow and CTO of Quantum-Centric Supercomputing at IBM. And we've had a long history of quantum at IBM. And in fact, dating back to maybe the mid-70s, the theoretical ideas of quantum information theory really came out of IBM research. But more recently, we've been really focused on building and bringing this technology to life and really making it a part of computation. It was 10 years ago that we actually put our first 5-qubit superconducting qubit quantum processor on the cloud. And then since then, we've deployed cumulatively over 90 quantum systems. We've built an entire ecosystem around an open source software stack called Qiskit. And we've been really pushing the envelope in terms of a very transparent roadmap of what we can deliver in terms of capabilities and hardware, as well as software that builds on top of it. But from a fundamental point of view, we see the drive of quantum as delivering the most performant capabilities and platform, being hardware and software, and then on top of that, building the ecosystem to get those involved with using it as part of computational workflows and really unlocking the value towards enterprise usage.
Axel?
Yeah, thank you. Likewise, happy to be here. My name is Axel Müller-Groeling. I'm a board member of Fraunhofer-Gesellschaft. Fraunhofer is the largest European applied research organization. And the mission is to benefit society and economy. And what did we do? What's our role in quantum computing? We formed 6 years ago a competence network with 23 of our 74 institutes on quantum computing with their specific research areas and their domain expertise, actually. And according to our mission, our aim is to see how do we get real world value out of quantum computing, right? And for that, as was just mentioned, we need the ecosystem. We need not just hardware or just software. We need also use cases. We need application. We need a lot more than just a single dimension. No? And to form that bridge from the potential of quantum computing to real-world value. That is the idea that we try to help with. And in that sense, we are also trying to be a technical advisor, if you wish, because just by definition and by our role and mission, we have on the one hand deep expertise in technical issues. On the other hand, we talk to industry all day long, and we know and think we know the needs of industry. We are talking to Airbus, to BMW, to Thales, to Infineon, to E.ON, to PwC, and the like of those. And that's the way how we try to push the whole topic forward.
Very nice. Thanks also for the intros that you've provided. I said at the beginning we're living in very interesting times, specifically with respect to the age of quantum and the age of quantum advantage. We've seen also in the latest report that we as McKinsey have issued around the state of the quantum industry itself, that during the last year we have seen an increase of 6.3x in terms of the investments. So we now see yearly investments of 12.6 billion into the quantum industry. We also see that this is not a one-off event. We see this as the new normal. And at the same time, we see this is not just pure academic research any longer. This is to a large extent also driven by private investment. And what we also see is that within the quantum computing industry, we've by now crossed also 1 billion revenues. And 1 billion revenues not just coming from, again, sort of state-owned programs or state-affiliated programs, but really also to a large extent from corporate customers who are investigating the topic, not for immediate quantum advantage, but in order to basically see what can the technology do, what would be possible IP to capture in that space. So we see that more than 300 of those companies also exist by now on a worldwide basis, and the number is further increasing time over time. And we also see very successful additional entries into the market with some of the recent IPOs and also the investment rounds that we have seen on the quantum side that essentially underpin that we're not just in a phase where the quantum computer will come in 5 years, and in 5 years we'll say exactly the same, but quantum computing is a reality that will come. And that companies now also need to prepare for, and not just from a security perspective, but also from a perspective of what can we actually do positively with the technology then also going forward. One of the key questions that essentially is out there is always, okay, when will we have quantum advantage? But quantum advantage is also a bit of a hype word because many people have claimed quantum advantage in the past. Many people say sort of quantum advantage is something that is very hard to reach. Also because the definition of the actual quantum advantage is not very clear. And maybe, Jerry, you just want to give it a first shot because I think IBM had been at the heart of some of the initial discussions around quantum advantage. So maybe you just want to contemplate a bit on what does quantum advantage actually mean for you, and when do you think we will have quantum advantage?
Yeah, sure. Thanks a lot for that prompt, right? I think there's really, there's a couple of feelings about quantum advantage. I mean, on one front, it's a very academic pursuit, right? That there's a kind of provable, verifiable way to show that a quantum computer can have an advantage over any kind of, any kind of classical solution, be it, cheaper, faster, or more accurate. But a lot of that kind of pursuit really is one where it's about showing the rigor and showing the verifiability through all kinds of scientific exploration. But I would almost want to say that that's one axis of advantage. And another one, there's really just bringing quantum to reality and bringing quantum towards real problems. And that we're seeing day by day, all the time these days, where we're seeing the application of using quantum for science that matters for real problems. Simulating molecular structures of sizes that are beyond what you can exactly simulate. Looking at things such as scientific problems such as neutron scattering, which are actually done in real laboratories, being simulated on quantum computers. We're really starting to see the way that science is being done on these machines in ways that hasn't been done before. And from that perspective, there's almost this advantage which is driving the reality of using quantum, where we're now beyond where we're talking about, science of the devices, but we're talking about how we're doing science on the devices for advantage.
Yeah, if I can maybe jump in on that particular take of on quantum advantage, I would say that I fully agree that we need to focus on practical problems. Like in the past few years, people were claiming quantum advantage on maybe problems that are too academic, that people don't really care about, that would not bring value in the end. And I would then align that with a recent example. I think IBM and Pasqal share the same perspective on that. It was covered in an article, a news article by Nature a few months ago. And it was about using quantum processing units, IBM one in one case, Pasqal one in another case, to describe the behavior of real material. So this was a key thing that happened, that quantum simulations on a quantum computer was for the first time able to reproduce the real behavior of a real magnet, a real material that was of interest for scientists, for R&D researchers and all. So we have already entered this era where you actually gain some unique insights using a quantum processing unit compared to what you could do with the GPUs or CPUs, with the best classical algorithms running on it. So in that perspective, I think we are already entering this practical advantage area where you can use quantum machines as a unique tool to study science and industry.
And I think, Axel, you had already mentioned that you have numerous discussions also with some of the industry leaders around then also the application of quantum. I presume that you will have the same discussions also around the AI topic itself, and therefore sort of what are the use cases. So maybe you want to elaborate a bit on what are the discussions that you have with them on quantum, and how do they also relate to some of the new questions that are now coming up in the age of AI?
Well, you see, in the logic of what I just said about Fraunhofer, what we take is a very pragmatic definition, right? Is there is there value, a relevant problem that creates value in the economic space that can be solved by quantum computing nowadays better than any classical computer could? That is more or less what matters for Fraunhofer, right? And matters for our customers. Yeah, they realize with interest that there is progress and that there's progress in certain scientific questions. But right now, we don't yet see a problem solved that is really of importance for a large company or a small or medium-sized company. And I think the confidence grows that will happen one day. Yeah? But I think also we don't really know how long it will still take, and I think it will not be the one moment or the one date or so. It will be a laborious path in which software, hardware, use cases, data, hybrid workflows, HPC capabilities will have to come together to really solve something in logistics, in manufacturing, in financial modeling, in chemicals. These are typical areas where we expect something, but we don't have it yet. Yeah?
I mean, I might want to add to that a little bit and just kind of say that I think one big thing though is it's not the right time to necessarily sit down and wait, right, for things to happen. It's really about how to actually start to use these tools. In many ways, the situation we're in with quantum is there's a roadmap, right, towards machines that'll be at a scale that we can solve problems which you can prove with pen and paper, right, at a scale with the number of qubits that we would have, with the number of operations. And that requires building towards what are called error-corrected fault-tolerant machines. But what's also, really interesting about the time that we're in right now, and to Loïc's point, and what are being built and deployed, are that these machines are at a scale at hundreds of qubits, running thousands of operations that are beyond what you can exactly simulate with classical computers. But what's that good for? We need to have the users to actually explore how it interfaces with HPC, how it ties in with workflows that are pushing the limits of solving problems in chemistry and optimization today to find that kind of heuristic advantage. And that's why it's really such an exciting time that we have the capability to deploy these. They have the capability to build on top of it to find the algorithms that will really define this this current phase.
And maybe Loïc, since we also see that many people are currently massively interested in what are the compute capabilities of a quantum computer, but at the same time we see that we have this massive need for additional compute capacity also in order to run all of the AI models that we're currently developing. How do you see the interrelation between AI and quantum?
Yeah, well, I think it's a very interesting question, and we should not try to oppose AI with quantum. It's really important to have to understand the complementarity between those two approaches. One example is right now with the machines we have, they are very good at problems which have a high complexity, but low inputs, low outputs. So this is the kind of things that quantum machines are good for. And this is complementary to what AI can do, which is typically big data sets, maybe not so much about the computational complexity of the task, of the underlying task, but really about large-scale models. So we really need to think about the complementarity between the two ways of compute. And actually, when we talk about quantum advantage, this hypothetical holy grail that we are all pursuing, there is a high probability that when a company goes live in production, what they will implement will actually be a hybrid workflow using CPUs, GPUs, QPUs. There is no, there is a relatively low probability that it will be only a QPU-only task. It will be something that will be distributed among the various sources of compute to actually try to leverage the strength of each. So that's our vision of actually how it will be deployed at scale in enterprises.
Yeah, and I'd like to just add on that, right? I think the wrong thing to think about is that it's AI versus quantum, right? AI, if anything, is an application of computing. It's an application of the resources that you have to help you compute. And to Loïc's point, it's really about how are these different processors handling math that is useful for computation. CPUs, of course, we know they're good at basic math, addition, and so forth. GPUs, of course, enabled a lot of what we can do with AI today with language models, and a big part of that is they're phenomenal at doing tensor math. QPUs, this is where it comes in terms of providing a differentiating computational capability of computing quantum circuits. It's a different language that we can use and leverage. And so it comes down to how do you actually best use all of these. And from the AI perspective, there's a lot to be gained both from finding the right types of algorithms where all three of these can influence AI. And at the same time, there's a lot going on in terms of using AI to find new algorithms and find new ways of using quantum circuits better for solving problems.
Well, I mean, on the surface, these are two different technologies on the surface, first of all. But they are competing. They're competing for funds. And right now, I'm afraid AI is in the advantage in that competition right now, because AI delivers real-world value, and everyone knows it, and everyone sees it, and everyone feels it. So we have to struggle a little here at this point. If one want to make the connection, and some of that has been mentioned already, I think one connection is sort of trivial, quote unquote, that is that AI will help to design better software and better hardware, and I'm sure it does as we speak. That's the more trivial connection. There is one that is potentially, I think, deeper and more profound. That is, right now AI is based on classical neural nets, and one could think of quantum neural nets or quantum spin glasses, basically, which may have a great advantage over classical neural nets, because the information content is much, much higher that you can store in such a quantum neural net, and also the training could be much faster and much more efficient due to things like tunneling effects and what can happen in quantum systems. So that is in the infancy, as far as I know, at least. But it is building one giant on the other, basically.
Yeah, I think so. You mentioned we mentioned the AI for quantum, designing algorithms, procedures, quantum for AI, like quantum neural nets, for example. I think there is also the area where you use data that is generated by a quantum processor to feed in a classical procedure. I think this is a very exciting emerging intersection between AI and quantum, especially in fields like material science, for example, or chemistry, because AI struggles because it doesn't have access to the ground truth, which is inherently quantum mechanical. You have to understand quantum mechanics to actually predict the reactivity of a material, of a molecule. And this is an area where quantum computing naturally fits in. And you can use these wonderful machines, our quantum computers, to create data sets that are completely new, that you cannot create in any other way, because there are no approximations. It's really quantum mechanics, raw quantum mechanics. And then use classical AI models on top to train on that quantum data. I think this is a very exciting area of research right now, and complementarity between AI and quantum.
Axel, maybe one more question, since you already mentioned the competition for funds between quantum and AI. One other competition that we also see is that a lot of the funding that we currently see for quantum essentially also goes to US-based companies, while sort of there is definitely a push then also on the European side for, can we build sovereign players, can we build sovereign supply chains? How do you see it in terms of what would actually be required? Do we require this to be a sovereign technology? Do we require dedicated supply chains? And how should we deal with this?
Well, I would say what we need to do, or what we need to be in Europe, is a competent partner in this game. And I mean both, competent and partner. And competent means that we need to have our own hardware technology, our own software. I think that is necessary, and we should strive for that. But we cannot strive for autarky, right? That doesn't make much sense. It's not efficient and will not bring us forward. So partnership and being part of the international ecosystem and have joint development projects, etc., be open to that is likewise important. Yeah? Competent partner. One could put it that way. I mean, you have to bring something to the table, you know, to be in the game, but you also have to be able to stand up from the negotiation table if something goes wrong. So you have to create your options. And I think that is the core of the sovereignty discussion, actually.
And maybe, Jerry, we already, before we started, we talked about your center also in Ing, and how do you see it, and how is IBM also dealing with the topic?
Yeah, so I mean, like, we are a global company at IBM, right? And we are certainly looking to partner all around the world. And a big part of, in fact, how we've worked to deploy these machines and put them on the cloud is to give that access, right? And also, in fact, we've been deploying systems all around the world in various different client locations. We have a data center that's in Ingen in Germany. We've deployed multiple systems in Japan, and one of them in the Supercompute Center there at the Riken Institute. And at the same time, trying to build ecosystems around that. Right? I use Japan as a real fun example because there, we're deeply engaged both in driving the kind of algorithm discovery and the application work on top to build, you know, software tools and to drive applications. And also, we've been trying to work with the local ecosystem to build hardware supply chain vendors, right? Where there's really, you know, a lot of the technologies that can be built, especially looking forward for what we need. There's a lot of opportunities there for you know, economic development in these local areas to help bolster everything that we want to make, right? And so, you know, there's really truly I'd say a ecosystem to build in these various different locations. Japan being one example, and certainly, you know, we look to do similar here in Europe.
Maybe Loïc, one other question that often comes up is, you already mentioned some of the use cases that one would have for the technology, specifically also in terms of actually performing material research. Of course, sort of there are many use cases for quantum computers that would be out there. What are like the key use cases for you, and what do you believe will be the first ones that would actually become reality?
Yeah, well, that's a great question, top of mind for us, for our team, of course, because we really want to target those use cases that will come first. We do believe that the things that are related to quantum simulation, materials, chemistry related, will be the first to actually be benefiting from the use of quantum computing. But beyond that, of course, we need to expand. The technology, quantum computing has a tremendous potential. There are a few use cases that we need to prove that we are completely dominating other sources of compute, so that we can show the value and iterate and find the new use cases, new verticals, and so on. At Pasqal, we are focusing on a few key verticals to work on. First one being the financial services, financial industry, because it's an industry which is very eager to use new technology. There is a lot of things that can be tackled using quantum computing, so we are working on that one. A second one is energy and oil and gas. So we've been working closely with energy partners in France with EDF, but also abroad with the Aramco in Saudi Arabia, for example. We have installed a machine, quantum processing unit, in Saudi Arabia, working very closely with Aramco personnel to find new use cases for the energy industry. And we also have, of course, logistics, as something that is of interest for us, for example. But those, I would say, are the main three, like quantum simulation, materials, chemistry, financial services, energy, which are really the top focus for us right now.
Maybe Axel, sort of, what are you hearing from your industry conversations on the topic?
Yeah. There is one class of problems which I would probably call optimization problems, and then logistics, manufacturing, energy systems would probably fall into that category. Where I'm not so sure is whether we really see the best of the quantum advantage in this class, actually, because classical solutions are not so bad in that. Yeah, the difference to the theoretical optimum is small. So I'm not so sure that this will be the breakthrough, so to say. There's another class of where one could say, okay, here we could find solutions which otherwise could not be found. For example, life sciences or pharma, drug discovery, for example, or the famous protein folding issue. Yeah? That is really hard for classical approaches, and here quantum could really bring a significant step forward. Materials chemistry, true, also. Financial modeling seems to be, in my view, somewhere in between. It has aspects of optimization, but it is also very hard due to the correlations. No? So if you want to simulate asset portfolios or equity values or so, there are correlations and they are dynamic. Yeah? The correlations are not static. So that is, in terms of physics, I'm a physicist, it's a many-body problem with changing rules of how things interact. Yeah? That's really complicated. So here probably is a very complicated but possible case for quantum advantage, I think.
Yeah, so from certainly my perspective, right, a big direction is, it was already said many times, but the material side and looking at chemistry, right? That's just, I think we've always heard that about being kind of Feynman's dream, right, of using quantum computing to look at these types of highly complex quantum mechanical molecular structure. And we were actually seeing that already in many cases. For example, in our recent published work with the Cleveland Clinic and working with the Riken Institute in Japan, actually simulating proteins out to 12,000 plus atoms, right? Using a quantum-centric workflow where we're able to take this large molecule, use a supercomputer to fragment it down to pieces that can be simulated on a quantum computer and then diagonalize on a HPC. So there's really, the potential there for a lot of this to push towards that molecular structure direction. Industries are looking at it, from the perspective, for example, Boeing, one of our clients, looking at, better materials that are resistant to corrosion. Moderna looking at, various types of materials that are, biologically relevant and so forth. But also, I think, these other directions that have been mentioned, I wouldn't write them off completely, in terms of optimization. I think there's a lot. In fact, there are working groups that are looking at this in terms of what are those kind of problems that we know are certainly very challenging for classical, and there are probably some classical solutions, but have the right kind of structure that can work well on a quantum computer. And last year, with a large industry optimization working group, we actually published a paper of what are the best kind of candidate optimization problems to look for. And it kind of is like a list to kind of start to work through and try to benchmark as we improve our quantum capabilities to work against. And then one third area that I do want to point out also that I think is very exciting for me is partial differential equations, right? And so partial differential equations are behind so much of so many problems that we have that we rely on. Weather modeling, fluid dynamics, and things like that, which are really computationally intensive. And there's been a lot of work here in terms of algorithm discovery to really push what can be potentially solved on quantum computers. Last year, there was a paper that really, brought in the idea of doing something like a 1D Navier-Stokes. And we expect to see more, right? So this is a part of the exploration phase where we're really excited to see algorithmic development. Part of that is done, in a way where you can do the math and you prove it. Other ways is really by using the machines and really trying things and, finding those kind of heuristic algorithms that drive advantage.
Thank you. I think when I was much younger and starting physics, I had 3 dreams during my lifetime: to see a flight to Mars, to see the room temperature superconductor, and to see the quantum computer in actual reality. I've given up on Mars. I've not fully given up on the room temperature superconductor. I'm fairly certain that I will see a quantum computer in actual reality. But I think this shows that essentially taking a bit the look forward and to look what the future will bring is something that is crucial also in order to see what is the potential of the underlying technology. So maybe if you would look 5 years ahead, Loïc, what would be the future vision and what do you think will be a reality by then?
Yeah, well, thanks a lot on this. Actually, so if we, before looking at the future, if we just look at the present right now, what has changed and what it will enable for the future, I think it's the right way to look at this problem. Because in the past, quantum computers were things that were really restricted to very few people on Earth. Specialists, PhDs in physics, really running a machine, and very complex machine which was mostly not working, and that we tried to make it work maybe 1% of the time to get one hero result. And right now what we have is a fleet of machines, like IBM machines, that are accessible through the cloud. They were the pioneers actually believing that by putting those machines in the hands of people, you could get something useful out of it. Right now, there are all the modalities that can be accessed. If you just have an internet connection, you can use quantum computing machines right now, Pasqal machines, IBM machines, and that's really I think what we will see is that the algorithm development and use case applications will transition from specialists like ourselves, the team at IBM, the team at Pasqal in very specialized institutions, to actually having something that is developed by the end user themselves. So I expect that we'll see more and more demonstration of quantum advantage in the next few years. And in 5 years from now, what we will see is every day new advancements that are created by the end users, and something like an industry, an ecosystem that is autonomous in using those machines. Very much like what we see with AI right now. It's you have the hardware, you have the infrastructure, the low-level software, and you have this explosion of applications and companies working on top of it. And so that's what I expect to be happening with quantum in 5 years.
Jerry, do you want to explain your future vision?
Yeah, no, so I mean, like, I think, we at IBM have a very concrete view of certainly the next few years, right? So we have targets for building and deploying a fault-tolerant quantum computer at the scale of 200 qubits and running out to 100 million operations by 2029. And then, beyond that, we have plans for in the mid-2030s to build a 2,000 logical qubit machine that can run out to billions of operations, right? We're kind of pushing into that cryptographic relevance type of machine. And this is all, our roadmap is very much grounded in the technologies that we're building and the innovations that we know that we need to hit from an engineering perspective to get there. And so, we're confident in that, especially as we build various devices year after year. But also, I think it's really exciting to just look at this transition as we move forward. That part of how we use these and how we solve problems with quantum, we hope really becomes more and more mainstream. So as you mentioned, right, that like it becomes a tool as part of your computational arsenal, right? Not unsimilar to how GPUs went from just being gaming modules to helping you get superior graphics in your digital movies to becoming the computational tools that they are today. We see that similar evolution, hope for that similar evolution, for quantum, right? That we get this algorithmic scientific push by using these as tools next to the best computational pieces available. And I certainly hope that in maybe the 5-year timeline, that becomes more and more relevant. And maybe you have your agentic workflows that are calling quantum computers or to solve problems as part of your workflows. And then beyond that, into 10 years forward, I hope that you don't even need to know that there's a quantum computer behind solving some of your problems, right? In fact, it's all hidden underneath the layers of you're just being able to solve way more in terms of the problems that you're able to address.
I can only emphasize what has been said already. If I make that comparison between AI deployment and quantum computing deployment, if I just narrow it down to just my own Gesellschaft, to Fraunhofer. Yeah? At Fraunhofer, everyone knows that AI is relevant. I mean, everyone in the world probably knows. But still, we need a lot of training and education and have all sorts of formats to exchange best practices inside Fraunhofer. There's still a lot to do so that even AI can be used as an everyday instrument to its best potential, so to say. Now, quantum computing, we know quantum computing will matter, but in Fraunhofer even, I'm not sure that too many will undersign that this will matter in 5 years. Yeah? Of course, there are those that are dealing with it. So, but we will need a similar effort, and I hope in 5 years we are there, that really disseminates all the technology that is necessary, all the thinking that is necessary, all the methods that are necessary to use quantum computing, which is not trivial at all. It's not just normal algorithms, as we know. We need to understand a lot more, or at least have software layers that make it easy for everyone, at least that. Yeah? And then bring it to every single of our 30,000 employees in the end, because it will be one of the most powerful instruments you can imagine, right now at least. So that is a long way still, but I hope in 5 years we are more or less at the stage where we are right now with AI.
Thank you. I think then, if I should summarize a bit, sort of what I think sort of I have at least learned during the panel that we had today, I think sort of the first thing is I learned that quantum advantage is not about theoretical problems, but actually about solving practical business problems and creating practical business benefit. And this may be a bit harder than doing this for theoretical problems, but it will definitely also be more rewarding than also for the industries. I was very impressed essentially also to see within this round, I mean, we're all coming from different backgrounds, that I think, Axel, you mentioned sort of the spirit of partnership is still there, that we should essentially try to solve the difficult, both scientific as well as also engineering challenges together, and that we should really see ourselves as competent partners who would be able to then also solve the corresponding problems together. And what I feel is there is a lot to come then also, as we discussed, also in terms of the respective use cases, specifically in some of the key focus industries around chemicals, pharma, financial services. This is not the time to wait. This is the time to act. And this is a time where we now see also an inflection point in terms of the commercialization of the underlying technology. So everyone who will say the quantum computer comes in the next 5 years and I can lie myself down for the next 5 years will definitely do a mistake in terms of the future business performance. I think this was a very energizing discussion, at least for me. I think what I definitely also take away from here is the best is yet to come in terms of real quantum advantage, in terms of the usage of quantum computers. I think, Jerry, you said sort of whether we actually use a quantum computer in the background or not should not be something that actually matters to the actual solution of the problem. So I'm definitely looking forward to a very interesting age where we'll be able to solve some of the problems that we cannot even imagine today. So with that, I'm very much looking forward to the future. I would like to thank you for your kind attendance during this session, and I would like to thank Axel, Jerry, and Loïc then also for having this panel together with me. Thanks a lot for this.
Thank you. Thank you very much.